questions facing science today. And today, wow, we've got a fantastic prompt from one of you, a listener, that really cuts deep. It challenges the whole idea of scientific rigor itself. The question is basically, how can we possibly insist that new ideas, new theories have to meet the strict standards of the current cosmological model that's lamb.cdm when that very model seems, well, fundamentally broken? As you put it so well, rigor means nothing if your base is incorrect. You've just been doing the wrong thing rigorously. That really struck me.
It's a fantastic place to start, honestly, because it perfectly captures the bind theoretical physics finds itself in right now. Look, the standard model of cosmology, lambda.cdm, is the best description we have, technically. But critics are increasingly saying it's not really a predictive theory anymore. It feels more like a post hoc framework.
Yeah.
It works by tweaking parameters, adding bits and pieces after we find something that doesn't fit, rather than predicting things from first principles.
Right, it's like patching holes rather than having a solid foundation.
Yeah.
And the big dream it's completely failing at is that holy grail, isn't it? Unification.
Precisely. The ultimate goal is always that theory of everything. It has to bring together general relativity, the physics of the huge, like gravity and space-time and quantum mechanics, which rules the tiny subatomic world, but lambda and CDM. It just doesn't have that internal coherence. Try to describe something like a black hole, where you need both GR and QM working together. The model just, well, falls apart.
And the evidence for this falling apart isn't subtle, is it? We're seeing this pileup of physical anomalies, things that just don't compute within the lambda CDM framework. These aren't small tweaks needed. These observations seem to, as the listener pointed out, break the lambda CDM model completely. We're talking about huge things like the Hubble tension, this disagreement on cosmic expansion, and weird things like Jupiter's core being fuzzy instead of solid. And then there are those impossibly big, impossibly old black holes that just shouldn't exist so early in the universe according to the standard timeline. The list keeps growing. These inconsistencies are practically screaming for a new way of thinking, a new architecture, which is exactly why today we're diving deep into an alternative. The Superfluid Universe Framework, PSUMOT, a potential unified hydrodynamic solution. Okay, let's properly unpack this standard model first, lambda CDM. Just to make sure we're all on the same page, remind us, what does this model say the universe is actually made of?
Right. So according to the latest data, all the stuff we see and interact with, stars, planets, gas, dust, well, that's ordinary matter. And it makes up less than 5% of the total energy content of the universe.
Less than 5%? That's wild.
It is. The vast majority is, well, invisible and, frankly, mysterious. We attribute about 68.3% to something called dark energy. That's the lambda part, the cosmological constant. It's driving the universe's accelerated expansion. Then, about 26.8% is attributed to cold dark matter, or CDM. This provides the extra gravity needed to hold galaxies and galaxy clusters together. But, and this is crucial, both dark energy and dark matter are essentially placeholders. They're names we give to effects we observe, not substances we've actually detected or fundamentally understand. We're inferring their existence to make the model fit the observations.
So the problem isn't just ignorance about 95% of reality. It's that the model itself feels engineered, reactive. You called it a concordance model. How did cosmology end up building this sort of reactive framework?
Yeah, concordance is the term often used. It basically means it was built piece by piece to fix problems as they arose. Think about it. The original Big Bang model had issues explaining why the universe is so smooth and flat on large scales. So cosmologists bolted on the idea of cosmic inflation, this incredibly rapid expansion, right at the beginning.
An add-on, okay.
Then galaxies were seen spinning way too fast. They should have flown apart based on the visible matter, a fix. Invent cold dark matter, this unseen stuff providing extra gravity, another add-on. And finally, when observations show the universe's expansion was speeding up, not slowing down, they dust off Einstein's old cosmological constant, lambda, and plugged it in as dark energy to provide this repulsive force.
So it's like building a car by adding parts whenever something breaks, rather than designing it from a blueprint.
That's a pretty good analogy, actually. It's not a single, elegant theory flowing from one deep principle. It's more like an assembly kit put together to make different, sometimes conflicting observations agree. And because it's built this way, this fragmented structure means it fundamentally fails at that biggest task, unifying general relativity and quantum mechanics.
And this fragmentation, this lack of a solid base, leads us straight into maybe the most embarrassing problem in physics, the cosmological constant problem, the CCP. This isn't just a minor oops, is it?
Oh, absolutely not. It's a catastrophe, a fundamental crisis.
Yeah.
Here's the issue. Quantum physics, specifically quantum field theory, or QFT, predicts that even empty space shouldn't be truly empty. It should be fizzing with quantum fluctuations, virtual particles popping in and out of existence. This activity should give space an inherent energy density, the zero-point energy, or ZPE. When QFT physicists try to calculate this vacuum energy, the number they get is staggeringly huge.
How huge are we talking?
We're talking mind-bogglingly huge.
Yeah.
So big it should warp space-time into basically a tiny ball. But when astronomers measure the actual effect of vacuum energy via cosmic acceleration, what we call dark energy, or lambda, the value is minuscule, tiny, almost zero in comparison. The difference between the QFT prediction and the observed value is, well, it's wrong by somewhere between 60 and 120 orders of magnitude.
60 to 120 zeros. It's hard to even comprehend a mismatch that vast.
Yeah, it's often called the worst prediction in the history of science. It's like, imagine you try to weigh a feather, and your scale tells you it weighs more than the entire observable universe. That's the kind of mismatch we're dealing with. It shows that our two main pillars of physics, QFT and general relativity, are fundamentally incompatible at this basic level. They give violently different answers for the energy of empty space. It screams that the underlying assumptions, the base, must be wrong, no matter how rigorous the calculations on top of that base are.
The problems aren't just buried in the math, though. They show up on scales we can actually observe. You mentioned a broken link on the cosmic scale.
That's right. We use the cosmic microwave background, the CMB that's the afterglow of the Big Bang, a snapshot of the universe when it was only about 380,000 years old to calibrate the lambda CDM model. We basically set the initial conditions using the CMB. Now, if the model's physics is correct, it should be able to evolve that early state forward 13.8 billion years and accurately predict the universe we see today, its expansion rate, its structure, everything. But it doesn't quite work. The parameters that fit the early universe, the CMB, don't perfectly predict the late universe, today's expansion rate, for instance, which leads to the Hubble tension. It suggests the physics connecting the start to the present is incomplete or just plain wrong. The link is broken.
Okay, so it fails on the grandest scale, but it also fails when we zoom in. You mentioned the cusp core problem related to cold dark matter.
Yes, this is a failure right at the heart of galaxies, especially smaller ones. The C in CDM stands for cold, meaning the hypothetical dark matter particles are slow-moving and, crucially, collisionless. They only interact through gravity, not by bumping into each other or exerting pressure. When you run computer simulations, these are called n-body simulations, using these assumptions, they consistently predict the dark matter center of galaxies, forming a sharp spike in density, a cusp.
Makes sense. Gravity pulls things to the center.
Exactly. But when astronomers actually measure the distribution of mass in real galaxies, particularly dwarf galaxies where dark matter effects should dominate, they don't find that predicted cusp. Instead, the observations show that the density profile is flatter in the center. It's a constant density core, not a sharp spike.
So the simulations say spike, but the universe says flat core.
Precisely. That simple assumption, cold, collisionless particles, just cannot reproduce what we actually see. It's strong evidence that dark matter isn't just simple non-interacting stuff. Maybe it interacts with itself, maybe feels some kind of pressure. Whatever it is, it behaves differently than the CDM part of lambda CDM assumes, especially on these smaller galactic scales.
Okay, so the theoretical foundations are shaky, riddled with problems like the CCP and the cusp core issue. And these cracks are widening because the universe keeps showing us things that just don't fit. Let's talk about these observations that are really pushing for new physics, starting with the Hubble tension. You said this could be seen as cosmic turbulence.
Yeah, the Hubble tension is probably the most talked about crisis right now. It's this stubborn disagreement about how fast the constant, h naught. We get one value, around 67 or 68 kilometers per second per megaparsec, when we measure it using signals from the early universe, specifically the CMB, and something called baryon acoustic oscillations, BAO. This relies on the lambda CDM model to extrapolate forward. But when we measure the expansion rate directly using objects in the local modern universe, things like Type Ia supernovae and Cepheid variable stars, which act as standard candles, we consistently get a higher value, around 73 or 74 kilometers in PC.
And that gap between roughly 67 and 73 isn't shrinking with better data, is it? It seems real. Why is this such a fundamental crisis for lambda CDM?
Because lambda CDM is built on the assumption that the universe is, on average, the same everywhere, homogeneous, and looks the same in all directions, isotropic, and expands smoothly, according to a single universal rate governed by its overall composition. If both measurements are correct, and the data for both is getting very strong, it means the expansion rate derived from the early universe doesn't match the expansion rate we see nearby today. This breaks that assumption of smooth, uniform expansion. It implies either that the physics encoded in lambda CDM is wrong, or that our local patch of the universe is somehow special, expanding faster than the average. Perhaps the universe isn't as isotropic as we thought. Either way, it's a direct challenge that the standard model currently just cannot resolve.
Okay, let's shift scales dramatically now. From the cosmic expansion down to planets in our own solar system, you mentioned Jupiter's core discovered by the Juno mission as another piece of evidence against standard thinking. What should Jupiter's core have looked like, according to the old models?
The standard model for how giant planets form is called core accretion. It's pretty intuitive, kind of a reductionist view. Heavy stuff sinks. So the prediction was that Jupiter should have formed around a dense, compact core made of rock and ice, maybe 10, 15 times the mass of Earth. And this core should have been distinct, like a solid ball, with a sharp boundary separating it from the enormous hydrogen and helium atmosphere above it.
A cannonball of heavy elements, basically, but Juno's gravity measurements found something completely different.
Completely different. Juno's data revealed that Jupiter's core is, well, the best words are dilute and fuzzy. It's not a compact ball at all. Instead, the heavy elements are mixed way out into the hydrogen envelope, maybe up to half the planet's radius. There's no sharp boundary. It's a gradual transition to compositional gradient. And interestingly, it seems to be non-convective, meaning it's not churning like you might expect. It's more like a stable, layered structure.
Wow. So instead of a neat separation, it's all blended together. What does that imply about the physics at play? It seems to really favor fluid dynamics over simple particle settling.
Absolutely. It's a striking example right in our backyard that under extreme pressure, nature doesn't necessarily follow simple particle-based reductionism. The structure seems to be governed by complex fluid dynamics, pressure gradients, and mixing processes, not just by gravity pulling distinct particles into a neat pile. It structurally supports the idea that maybe we need to think about cosmic structure, even planetary structure, in terms of emergent fluid states, rather than just collections of particles.
And the final big observation that seems to, as our listener suggested, really break the standard model timeline, those ultramassive black holes found in the early universe.
Yes, this is another profound puzzle. Telescopes like JWST are finding supermassive black holes, billions of times the mass of our sun, that existed when the universe was incredibly young, maybe only a few 100 million years old. The problem is, according to standard lambda CDM cosmology and astrophysics, there just hasn't been enough time for them to grow that big.
How are they supposed to grow, normally?
The standard picture is that they start from the remnants of the first massive stars, stellar mass black holes, and then gradually grow over billions of years by accreting gas and merging with other black holes. But these behemoths we're finding, they're already huge, way too early in cosmic history. It implies they must have formed incredibly rapidly, or perhaps through some entirely different mechanism we don't understand, maybe even from direct collapse of huge gas clouds, bypassing the stellar seed stage. Some are so massive, so early, like they were basically already there before the first stars even had time to form, live, and die to create the seeds. It just completely messes with the established cosmic timeline.
That sounds like a direct contradiction to the Big Bang sequence of events.
It's a huge challenge. It forces us to rethink either how black holes grow, or how early structure formed, or maybe even the timeline itself. You know, the physicist Brian Cox mentioned that these objects are so confusing, some scientists were almost hoping they wouldn't find them, because their existence poses such deep problems for our standard understanding of gravity, space-time, and cosmic evolution. It really hammers home the listener's point. If your rigorous model can't even accommodate the existence of the universe's most massive objects within its own timeline, then that rigor might be applied to a foundation that's just not reflecting reality.
Okay, so lambda TTRM is fragmented, it's reactive, it's facing these massive observational crises. This brings us to the alternative we're exploring today, PSU-MOT. If the standard model's problem is its reliance on separate, mysterious particles, how does PSUMO approach it differently? What's the core idea?
The core idea of PSU mode is radical unification. It says, forget the dualistic picture, ordinary matter plus separate dark matter plus separate dark energy. Instead, picture a single underlying physical medium pervading all of space. This medium is called the quantum superfluid substrate. And crucially, PS mode identifies this substrate with dark matter. So dark matter isn't particles, it's the actual substance of space itself. And the really big shift is that the dynamics of gravity, cosmic expansion, maybe even particle physics arise not from particle interactions, but from the hydrodynamics, the fluid flow of this substrate.
A superfluid substrate as dark matter, and its flow governs everything. That's a huge conceptual leap. How does this single fluid manage to account for both dark energy and gravity, which seem like very different things